So, hello everyone, and good evening, and welcome all of you to this episode number 6 of Project Discussion Series, which is an online platform to discuss projects and to share our ideas, experiences, and thoughts and problems. So, this is the 6th episode, and first of all, thank you for taking out time and joining us live today. And also, thank you to those who would be watching this episode later on our streaming platforms. So, as you know, it has been 6 episodes. What we do is already known to us, so I'll not go into that. I hope my voice is audible properly and all is well on the technical side. So, today is a good day to conduct our session. Yes, sorry for that. So, today we celebrate the birth anniversary of our uh, former president, Bharat Ratna Shri APJ Abdul Kalam Sahab. So it is celebrated as a World's Student Day. So may we always remain student and may we keep learning, and whatever we learn, let us try to learn something new every day, and whatever we learn, maybe share with others. So that is what we can pray to God to give us that strength that we keep on learning every day. Good. So we will start with our first segment then. And as you know, our first segment is where we take up problems faced by structural engineers, commonly faced problems. So today we are taking two problems and we will discuss them. Let us see. So the first problem that we are taking up today is about whether to provide two-legged stirrups in RCC beams as per the software output or multi-legged stirrups are allowed. So this is quite a common problem that we face, and for this problem I must thank engineer Rahul Brijpuria, who was discussing this issue just a couple of days before, and that is how I uh, got this thought that it is a good platform to discuss this issue. So whether to provide two-legged stirrups in RCC beams as per the software output or multi-legged stirrups. That is what we are going to discuss today. So how many of you know that softwares usually provide two-legged stirrup in the output? So whether it is ETABS or it is StatPro, as a default, these softwares provide two-legged stirrups in their output. Okay. So what is the reason for that, and why all the softwares are providing two-legged stirrups, shear stirrups I'm talking about in RCC beam? So why is that? That is the first thing we would like to explore. So any before I just start, anyone knows why two-legged stirrups are recommended in the code? So if you read the code and if you read the special publication explanatory to the code, that is SP24, your code tells you that in case of torsion, whenever you have torsional movements, two-legged stirrups are required. Okay. I think all of us understand that shear stirrups are required for torsion and uh, shear. So when there is a torsion in your beam, you have to provide two-legged stirrups, and the stirrups have to be provided by this formula. So if you see on the screen, I am sharing the formula for providing the two-legged stirrups. So there are two components of this formula. The two formulae are given, basically one formula above, and in the next line a second formula is given. Why these two formulae are given? So those two formulae are given, and I have just written down some notes on the screen. So the first formula is to account for situations where you have a large torsional moment and relatively smaller shear. All right. So the torsional moment is quite large and shear is small, and to avoid mode 2 failure, that is a warping type of a failure in your cross section, I have tried to show the mode 2 failure on the right side of the screen. So to avoid such a mode 2 failure, only two-legged stirrups are effective. Do you get it? If you try to see this mode 2 failure on your right side of the screen, you will see it is a twisting plus warping combined behavior failure that is happening. And for avoiding this kind of a failure, what is most effective will be the two-legged stirrups provided on the periphery. So your code tells you that for these situations, internal legs or multi-legged stirrup may not be good enough. All right. So therefore, code is asking for two-legged stirrups. So if you read the first line, two-legged closed hoops are required. Then you have a second formula also, but the total transverse reinforcement shall not be less than. Why this formula is given to you? So this is to account for your normal shear failure. What is a normal shear failure? Where your entire cross section undergoes shear stresses and there is a failure along the depth of your cross section. So that type of failure, we will call it as the normal shear failure. So to account for normal shear failures, typically in cases when you have large shear values and relatively small torsional values. Okay. So this is the reason why two different formulae are given to you. Whichever gives you the higher steel, that steel has to be provided. So the first formula is for cases of large torsion and relatively low shear, The second formula is given for large shear and relatively small torsion. So we have taken an example to just understand this further, and I've just written down the analysis moment, mu, analysis shear, and analysis torsion. Let us assume that we have got these values from some software output. So there is one thing that you will notice in these values, and what is that? What is that one thing that you will straight away notice? So you will notice that this beam is having a large moment, it is having a large shear, but the torsion value is relatively small, correct? So it's not a very big torsion value that you have got in this beam. Compared to the torsion value, you have got a substantial shear and a substantial moment. And I have put the beam sizes 400 cross 600. Let us take M25 and FE500 and try to calculate the reinforcement. So we have just run down these values in our Excel sheet, and I have also noted some manual quick hand calculations. So if you see, this is as per the first formula. We have assumed a spacing of 100 mm center to center. So the SV value has been assumed, and rest is a simple calculation. So what we get over here is 10 dia bars at 100 center to center, two-legged stirrups. This is the requirement that we are getting. Can anyone tell me which, for what criteria was this first formula applicable? When did we need to use this first formula? So this first formula was to take into account the cases when you have substantial torsion and relatively low values of shear in your beam. All right. So our case, if you notice, is not a case of substantial torsion. We have a relatively small value of torsion. We only had a 8 kilonewton meter torsion as compared to the shear and moment. It was quite low. So therefore, you see that from this, my stirrup requirement is still manageable. I can manage 10 dia bars, 100 center to center, two-legged near the face of column. I can easily provide these stirrups. But now when I use this second formula, but the total transverse reinforcement shall not be less than. So you will notice that now if I have to maintain a two-legged stirrup arrangement, my area required is 123 mm square per leg. So even a 12 dia 100 center to center two-legged bar is not sufficient. Are you getting this point? So 12 dia stirrup 100 center to center two-legged, even that is not sufficient. We are having a shortfall of around 10 mm square per leg. So you may have to either go for a 75 mm center to center spacing, or then you may have to go for a 16 dia bar, or you may have to live with a shortfall in your reinforcement requirement. So this is what we are getting, and as a practical designer, we feel that it is unusually high shear reinforcement that we are getting. So what should we do? What should we do? So let us try to revisit the clause, and let us try to once again interpret it. uh, Ajay ji is saying Fy value should be 500. Okay, I'll just take up this issue. Let me finish. So let us try to reinterpret this. So if you recall what I had told you, that the first formula is for which type of failure? So the first formula is to take into account the high torsion, relatively low shear failures, when the failure is mode 2 failure, and when you require two-legged stirrups to take care of that mode 2 failure. All right. So for this first formula, two-legged stirrups are essential because it is to take care of the mode 2 failure. But if you look at the second formula, I told you the second formula was for high shear and low torsion. Now, if your shear is high and relatively torsion is low, in my opinion, you can provide multi-legged stirrups also. Do you get it? So you can provide multi-legged stirrups in that case. That is my interpretation. Even if you read the code, it is saying, but the total transverse reinforcement. In the first formula, it was saying two-legged closed hoops according to the first formula. And then it says, but the total transverse reinforcement shall not be less than. And then it gives you a second formula. So in my interpretation, you can provide a multi-legged stirrup for this formula. Are you getting this point? So if we interpret it that way, and I think it's quite uh, agreeable to me at least, because this formula, second formula, was for a case of high shear, low torsion. As I told you, the failure is one you get in normal shear failures. So multi-legged stirrups can be effective in that situation. So if you revisit your formula and if you revisit your calculations once again I will assume 100 stirrup spacing. For the first formula on your left, we will continue to provide a two-legged stirrup. So what you get is a 10 dia, two-legged, 100 center to center stirrup as sufficient. But in the second formula, I am going to allow multi-legged stirrups. Why? Because I just explained that this situation was to cater for normal shear failures. So even the multi-legged stirrups are sufficient, are effective in this case. So in the second formula, if you see on your right side, I have now used a three-legged stirrup arrangement, assuming, of course, that I have sufficient longitudinal bars to tie that. So for three-legged stirrup, I can get 82.3 square per leg. My total requirement was 247, providing three legs. 82.3 square per leg is required. So I can manage actually 10 dia at 100 center to center, three-legged, with a small shortfall of 4 square per leg. So in my opinion, I can say that this is okay. So if we interpret the formula in this way, then the shear reinforcement that I will provide will be 10 dia bars, three-legged at 100 center to center. So, so a slightly different interpretation of the same clauses gives us this particular output, which is acceptable to me. So as I told you, this is the interpretation as we see it. That means as I and we at AuxEn's see it, I and Akanksha were discussing this issue today. So this is the interpretation as we see it. And of course, it remains open for discussion. But I think this is a good interpretation that we have made. Yeah. So this is what I had to tell you about the first issue. I hope the discussion is clear what we discussed. Okay. So before I move ahead, so just to conclude what we have done, so we had two formulae given to us in the code. What I said is that for the first formula, we can provide we have to provide two-legged stirrups as per the first formula. But as per the second formula, you can provide multi-legged stirrups. Now after this, whichever is higher, you have to provide that. Okay. So if you are getting uh, critical values from the two-legged stirrup scenario, you have to provide that. If you are getting the multi-legged stirrup as critical, you can do that. See, when this situation comes under discussion, you have to understand when you have a case of low torsion in your beam and substantially high shear forces. You see the values I had taken. So there was a substantial movement, there was a substantial torsion, sorry, there was a substantial movement, there was a substantial shear, but there was very small torsion. But just because there was torsion, I have to use the formula given in the code, correct, which is this formula. So this situation I am discussing is the case where I have a beam which is having low torsion. Right. So this is what I had to tell you about this. Now we can have a small discussion on this problem before we move ahead. So Ajay ji is saying that we have to use Fy of 500. No, so it's quite clearly given in the code. Not for this formula, I agree. But if you look at the formula before, they have quite clearly mentioned that the Fy characteristic yield strength of your bar does not have to be more than 415. I agree that they have not once again written the characteristic strength not to be less than 415 for this formula which you see on the screen, but it's quite, I mean, it's quite understandable that what code is trying to tell you that Fy should not exceed 415. Parth is saying we can have torsion stirrups and provide two-legged and more legged for just shear. Correct. So that is what we, that is the similar conclusion that we reached. Rahul is saying, what if torsion is also high, say 50 kilonewton meter? No, so if torsion is high, I told you, if torsion is substantial, then your first formula will be the more critical. Your first formula will be the formula that gives you the more critical values. So you will have to ensure that two-legged stirrups are provided as per the first formula. All right, right. Then Nagesh is saying at times when torsion is high, we need 16 die stirrups also. Should we give it or convert it into multi-legged stirrup? Yes, the same answer. If you are using the values from the first formula, your stirrups have to be two-legged. There is no confusion about that, and there is no discussion about that. The discussion is that when you are going to find out stirrups as per the second formula, you may work out as multi-legged, and then finally, whichever is more critical, you can give that. Okay. Parth is saying, but second formula is taking tau VE, not tau V. Right. There's no problem with that because I told you that the second formula is critical when you have a high shear, low torsion situation. All right. So when you have a high shear, low torsion situation, anyway, because the torsion value is small, your tau VE and tau V will be similar. So code wants you to take tau VE, but the code has that understanding that tau VE and tau V will not be very different from each other because the torsion value is small. Good. So this is what I had to tell you about the first problem. So I hope we got some takeaways from this discussion. So you may use multi-legged stirrups, in my opinion, as per the second formula, and you have to provide two-legged stirrups as per the first formula. Whichever gives you a more critical value, those stirrups you have to ensure are being provided. Very good. So this is what I had to tell you, and this was our first problem. Now there is one more problem that I would like to discuss, and that is the situation. So this is now a problem from structural steel. The first problem was from RCC design. This second problem is from structural steel design as per IS 800 2007. So in a typical three plate section, when you have flanges and webs, if your web becomes slender, then what the software is able to do and what our code tells us, this is what we are going to discuss. Before I begin, is anyone aware what code tells us in cases when we have slender webs in our three plate sections? What are the codal recommendations? In case when uh, I have a slender web, what are the codal recommendations for me for design? So if your web is slender in accordance with table 2 of IS 800 2007, how to check for slender? We have to find out the dy tw values, and they have to be compared to certain values as per table. Right now I don't have sufficient time to explain these checks, but I think most of you are aware, those who do steel designs. uh, so what does our code tell us? So as Akshay is saying, we neglect the contribution of web in the flexure calculations, and for compression, we take the effective width. So I have highlighted the two clauses, the two relevant clauses for flexure on the right and for compression on your left. So I have highlighted the compression part, that you have to deduct the width that is over and above the semi-compact region. Okay. that is for compression, and for flexure you have to disregard the web, so the web has to be ignored. So I just tried to make a small sketch, and if you see, for compression you have to take the effective width. So over and above the semi compact, whatever remains, that you have to take as your effective width. So the effective width is d minus 42 epsilon tw whole into tw. This will give you the effective area of the web to be considered for compression calculations. And for flexural calculations you have to altogether ignore the web from your design. Okay, this is what your code says. I hope this is clear, what our code tells us. But now what softwares are doing, has anyone I mean, is anyone aware of the discussion that we are going to have? Has anyone tried this and faced this type of a problem before? Okay, if not, let us see. So what we have, after working on both the softwares using steel design, sorry, after doing steel design using both the softwares, what we have found out, that StatPro is able to design the section. StatPro is able to design the section for slender webs as per the codal provision. So StatPro disregards the web for flexural calculations, and for compression calculation it takes the effective width. StatPro does that quite well. But ETABS is not able to consider the effect of slender web. Okay, so ETABS is not able to consider that. Let us see how. So what we have done over here is we have made two identical models on STAD and on ETABS. Identical model, everything is identical, loading is identical, geometry is of course identical, and the member properties that we have taken are such. So we have taken a flange of 175 cross 10 and a web is 700 cross 6. So we have deliberately taken this section which ensures that your section is slender. And uh, we have taken all the other design parameters and we have adjusted them in such a way that there is no other discriminating factor. There are other issues also. In ETABS there is a issue that ETABS takes C1 and your STAD is not able to take C1 factor. ETABS takes the effective length properly. STAD is not able to do that. So we have removed all those other discriminating factors so that just the difference in calculation will be whether or not your software is able to consider slender webs. Okay, all other design parameters have been adjusted by us. All right. So what do we find? We have taken the same column in both the models. The bottom left corner column, if you see, being highlighted in STAD, the same column we have considered in ETABS also. So on your left are the on your left is the window where we have just highlighted the analysis results. Don't look at the STAD and ETABS written above. It's a mistyping. Anyway, so on your left are the analysis results. Both are identical. If you see 1 kilonewton here and there, it's okay. All right. The moments are similar, analysis moments about major axis and about the minor axis. So analysis moments and analysis forces are same. But now when we go at the design capacities, you will notice one thing, that STAD is calculating an axial load carrying capacity of 680 kilonewtons, but ETABS is calculating an axial load carrying capacity of 1095 kilonewton. Same column, remember, same cross section, same column, same length, everything is same. But ETABS is calculating axial carrying capacity of 1095 and STAD is only calculating it at 680. If you look at the moment carrying capacity, 263.54 as per STAD. Again, ETAB seems to be calculating the capacity as more. About the minor axis, both are giving me same values. So ETABS is over calculating the capacities. So what ETABS is doing is, ETABS is not able to consider the slender web provisions as per IS 800 2007. So this is a very important point because many of the engineers these days do the steel design using ETABS. So ETABS is not able to consider the slender web provisions as per the code. So to just ensure that we are doing everything correctly, we also cross-checked it with our manual calculations. So we have an Excel sheet made which checks the three plate sections in a very good way. So we checked our results on this also. So all the values that we calculated, they match with the stat calculations. If you see the capacities I have highlighted, the value is matching with the stat pro calculations. All the capacities match to the second place of decimal. So if you see the table that I am showing right now, design capacities as per stat in the first column and as per manual calculations in the third column are matching. ETABS is giving me over capacity. So why this is happening? Because ETABS is not able to consider the slender web effect. Now, if ETABS does not consider slender web effect, what will happen to the utilization ratio? Tell me. What will happen to the utilization ratio? Will it calculate conservatively or will it calculate the utilization ratio on unsafe side? What do you think? So if it is over calculating the capacity, you have to understand that it is actually going to under calculate the utilization ratio. Are you getting this point? Because it is over calculating the capacities, it is going to under calculate the utilization ratio. So now if you see in the first column, I have written down the stat pro utilization ratio 1.46. As per manual calculation also we are getting 1.46, but ETABS is giving me a 0.802 ratio. So that means if a structural engineer was doing the design on ETABS, he or she would say that the member is passing. Correct? He or she would say that member is passing as per ETABS because the ratio we are getting is 0.46, 0.802. So as per ETABS, the structural engineer would conclude that the member is safe, but actually the member is failing with a UR of 1.46. So this is a major problem that we find in ETABS. So ETABS is not able to consider the slender web. So all the ETABS users who are doing their designs as per, who are using ETABS for structural steel design need to be careful of this aspect. And especially when you are doing PEB structures, pre-engineered structures, because in PEB structures, the strategy is to provide slender webs. That is the strategy that most of the designers use to provide slender webs, and to take the shear they provide web stiffeners. So that is the strategy that they use. So especially if you are using ETABS for structural steel design, and especially if you are doing these types of structures, you have to be very very careful. Beware that ETABS is making this error in steel calculation. Okay, so ETABS, to conclude, ETABS is not able to do the design for slender webs properly as per the codal provision, leading to under calculation of utilization ratios. Good. So this was the second problem that I had to discuss. If anything, any discussion point we have, we can take them. Yes, anything anyone wants to discuss? I'm just flashing out the comments that we got. Yes, Kashaf is asking, can we rectify this? No, I tried to work my way around this, but it's we cannot rectify this in ETABS, at least as per the current uh, inputs that we have. So we cannot rectify this right now. Yes, someone was telling me that in select series also they are facing a similar problem. So I tried to check yesterday in select. Sorry, in Connect edition. Sorry, my mistake. Someone informed me that in Stat Connect edition also there is certain problems that they are finding, especially with slender web cases. So you those who are using those who are using Stat Pro Connect Edition, they just can check, and they can just take a section where the web is becoming slender and try to cross check the moment carrying capacity and actual load carrying capacity with manual calculations. Just try to do that. Ajay ji is asking what about MBS and Tekla. I'm not sure what MBS means, but Tekla, I am not sure what Tekla is doing. I can tell about ETABS and Stat Pro right as of now. What is MBS? I don't know MBS. Okay, good. So this was the second problem that we had to discuss. I hope these discussions were, uh, I mean, these discussions were worthwhile, and they could resolve some of your queries that you may have had. Now we'll quickly take up our second segment, and that is where we discuss some project or some issues related to the project that we faced. Okay. So this time, because we did not have any good problem to take up, we just thought that we will take up an interesting project that we did a few years ago. So that is what we are going to take up today. So why it was interesting, let me just tell the problem statement that we had. So we were our client was a big seaport, I mean an authority that was managing a big seaport in the state of Gujarat, and the client wanted a solution for protecting their coal heap. So their business was that they used to import coal from other countries, and then they used to stack that coal in the open, of course. But because it was a port, so you had a sea nearby, so the strong winds from sea would just blow off that coal, and those coal particles would then mix up in the environment. The particulate matter would mix up in the air, and that was causing a lot of environmental hazard. So actually they had a they had a directive from the environmental department to do something about the coal particulate matter that was getting mixed up in the air. Why that was happening? Because just the wind was blowing from the seaside, and it was blowing the coal particles away. So they needed a solution for that. So what did we do? So a wind barrier or a wind screen type of structure was thought of. This is not, I mean, it's not as if we for the first time thought about this concept. It's a well recognized concept to provide wind barriers or wind screens. So this type of structure was then thought and conceived, that we will provide a wind barrier, and the structure should not be completely opaque. Why it should not be completely opaque? Because then otherwise it will have to provide resistance to the large wind forces due to high wind speeds. Okay. So of course it was not supposed to be completely opaque, and we needed a solution whereby some of the wind could pass through and some of it would be I mean would be provided a barrier. So we needed a barrier, but we needed that it should not be a opaque barrier. All right. As Rijeshi is saying, wind barriers with vanes. Right. So we actually provided a similar uh, methodology or similar concept in this case. So the total length of the windscreen required was 1 kilometer, and the height required was 16 meters. Total length of windscreen which was required was 1 kilometer, and the height was 16 meters that was required by the client. So this was the sort of a concept that we proposed. So if you can see, it's a rough sketch that I have drawn. On your left side, you can see the wind blowing from your open ocean, and then on your right side is the coal they have stacked, and now you want to break the wind so that the coal particulate matter does not mix up in the air. So this type of wind screen was proposed, and this was the concept. If I just try to detail it more, so if you see, what we have done is, the main important crux here to be understood is what screen did we propose. So we proposed a deck sheet. I hope you all of you are aware of deck sheets. So we proposed a deck sheet, but because your general deck sheets are opaque, we proposed a perforated deck sheet. Perforations means having small holes in that. So we proposed a perforated deck sheet which would act as a wind screen, and then to I mean and then we provided a vertical system and a horizontal system. So we provided vertical trestles and horizontal truss elements. So I have written down the load path also, that the assumed load path was that the wind will first hit the perforated deck sheet. From there, it will go the load will go to the truss. From truss, it will go to your vertical trestle, and from trestle it will go to your RCC pedestal and eventually to ground. So this type of vertical wind barrier, wind screen was proposed. And in plan it looked like that. Of course the design was simple. We just had to design typical units like this. So you see the trestles were placed at 6 meters apart, vertical trestles. The height of trestle is 16-meter, and you can see the side view of each trestle. By trestle I mean the vertical column, built up column, you can say. So each trestle is 2.5 meter wide at the base, and it tapers down to 1.25 meters at top. And then we have provided horizontal trusses at every 4 meters. That is how the 16-meter geometry is done. So the load first comes on the deck sheet. From deck sheet, it travels to the truss. From truss, it will travel to the trestle. From trestle, it will go down to your RCC pedestal and ground. Okay. So this is how we did it. And we used hollow sections. This is a typical, this is a drawing that I'm trying to show you, the drawing that we prepared. These are the finished drawings. You can see some openings also because there were certain more complications involved. So we had to provide some entry exit points for trucks and vehicles and all those things. So there were some openings. Otherwise, it was completely covered with perforated deck sheet. So the key points, you can now see a perforated deck sheet. So it was custom made. You do not get perforated deck sheets as such because everyone manufactures your solid deck sheet. So it was a perforated deck sheet. It was custom made. First, the perforations were made in your plain sheet, and then that plain sheet was formed into your it was formed into your profile, and it was then hot dip galvanized also. Everything had to be manufactured in workshop because there was no permission to do any welding on site. So all the connections were to be provided as bolted. That is the usual, I would say, situation that you have everywhere in industrial units at least. Okay. So this was done, and then it looked something like this. So you can see the modules being assembled on site and connected through bolting. One figure that you see is of column pedestal being cast. Here you see the trestles erected. Also you can see some stubs, bracing stubs, where your new bracings will be bolted, and so on. And this is the perforated deck sheet that you can see in a close-up picture. So this was about the project that I wanted to tell you. An interesting project, not because it was difficult to do, but it was a different kind of a project that we did. Good. Anything about this? So Shrijesh ji is asking wind barriers with vanes. Yes, similar to that. Yes, I must introduce Srijesh ji over here. Actually, he is a naval engineer, and he is now a retired officer from the Indian Navy. So he was one of the engineers working on the design and execution of the recently launched aircraft carrier INS Vikramaditya. So he was one of the design engineers on that. So we are very happy and proud that Srijesh ji you could join us today on this episode. Good. So this was what I wanted to tell you about problems. If there are any questions, we can take them later uh, when we move to the open discussions. Now we go to our third segment, which will be experience sharing, where we invite uh, engineers, young engineers, and we try to understand from their experiences and try to learn from their experiences. So, in this episode, our guest engineer who is joining us is Engineer Arthur Thomas. He is a postgraduate in structural engineering, and right now he is working as a structural design engineer at Sterling Engineering Consultancy, Mumbai. So they are involved in design of medium and high-rise structures, both residential and commercial. So I invite him to join us today on this show. So I don't know if he has joined. Hello, Arthur. I'm not sure if he has joined. I think your video is off. Okay, so he's trying to switch on his video. I think he's facing certain. You join us again. What you can do is just uh, disconnect and join again. In the meantime, we can take some questions. So related to the related to the project that we just discussed. Srijesh ji is asking, how did you arrive at the size of pores? Right. So that size of pores, actually, it was, I would say, it was just an engineering judgment that we tried to make. So broadly, we made a 50% area. So 50% area we tried to provide it as pores. So that means 50% of the air will pass through and 50% of air will stop. So that is what we thought. And the size of pores basically we tried to finalize after the deck geometry was understood. So on the basis of the deck geometry, we arrived at the size of pores on the basis of the trough and the crest widths. But uh, I think the area came about 52% was your uh, pores and 48% remaining was the deck sheet. And then we also did load testing of this sheet. So we actually did some load testings to just check what is the flexural capacities we are getting of this uh, deck sheet with perforations. So that is what we tried to do. Okay, so I think Arthur is has joined us, and we once again invite him.
Hello, sir.
Yes.
Good evening.
Hello, Arthur. Hello, good evening. So,
Yes.
Arthur Thomas, he is joining us from Mumbai, and
Yeah.
thank you for joining. So, I already gave a short introduction of you.
Yeah.
So, he
Thanks
has
for that.
done his, uh, he is a post graduation in structural engineering, and right now he is working at Sterling Engineering Consultancy Services, and they are involved in medium to high rise structures, both commercial and residential. Hello, Arthur. So tell us
Okay.
about, uh, I mean, once you got out from BE till now, what you have been doing, if you could tell our audience in brief.
Yeah. Good evening, everyone. So right after my BTech, uh, I had done my MTech in structural engineering from Manipal Institute of Technology. Thereafter, in the first year it was an academic year, and the second year we had a project year where I got a chance to do a wind tunnel project at SERC Chennai. It was a wind tunnel studies on an aeroelastic model, and I had an amazing 1 year experience out there, learning from the scientists out there in that wind engineering laboratory. Thereafter, as a fresher, I was looking out for a job, and I got a chance to work at SN Structural Engineering Consultants, located in Mumbai itself, and I was there for a year, most 1 year, and I got a chance to learn different softwares initially, like ETABS, and I got more frequent with it in the usage of it, and RCDC, ETABS, and SAFE. And so that was my starting point of career, where even I got a chance to work on Stat Pro. So there were trainees out there. There were trainers out there who were training people. So I had a good experience out there. So then thereafter, I moved on to another consultancy firm named as Shilp Consulting Engineers, which was located in Goregaon, Mumbai. And there also I was involved in design of different RCC structures and proof checking of structures, and even I was involved in the quantity calculation of a big port. So I got a chance to work on quantities and preparing Excels regarding it, the same. Thereafter, I got a chance in the first two firms were kind of a medium size. Then I moved on to a big of a large size firm called a Sterling Engineering Consultancy, and I have been working in Sterling since the past uh, four 4 years. And here also my experience was amazing. And yeah, so currently I'm based here, and this firm is also located in Kurla, Mumbai. And here also I got a chance to work on steel structures, not exactly steel building, but I got an exposure to various auxiliary or miscellaneous structures like canopies and the portal gates and portal frames, cantilever portals, and chiller platforms, and many more some small strengthening works with steel members. So in that way, I got an exposure to at least explore on how steel design works, and which software we can use to design steel, and an exposure to even more depth in Stat Pro. And then I got a chance to work on then there was a period of COVID time where the projects were input were less, but then I got an introduction to Ashutosh sir and Kutamli sir, and his train as whatever courses were conducted, I used to join that, and I learned a lot from that. Though the projects shared by my firm were quite less during that time, but at the same time was improving my knowledge and skills by attending his lectures. And I had a great time in that period of time when I was working from home. So that period of time also was great. And then in my then the fourth year, it was in third and fourth year of the firm where I was in, Sterling. I got a chance to work on complex projects. Like this project is located in Gujarat, Ahmedabad, Gujarat,
No, so
and it's
before
yeah,
you go to complex project,
yeah.
we would just like to understand that, uh, I mean, what are your current roles and responsibilities at your current employer? Like,
Yeah,
how
so my
what you are
yeah,
usually.
so initially when I joined the firm, I got a chance to interact with clients, attend meetings. It was a project located in Mumbai itself. It was a residential structure, so there I had to have a meeting, attend the meetings at the client's office, and interact with the various architects, with the architect of the uh, structure and the MEP consultant. So there was a lot of coordination works going on, mails sent, and at the same time designing the structure. So that particular structure, like I was given both the responsibilities together. It was a small G plus 15-story structure, but I got a chance to, I mean, the coordination work and the design work, which is at times tedious, but both
Yeah.
was done by me. No team was given other than a draftsman. So
Yeah.
that was my uh, role and responsibility. Then thereafter, I got another project leader where the project started increasing. So
Okay.
then I was assigned a project leader, and
Okay.
then there were it was a large podium with 9 towers around connected to it. So
Okay.
that had a big team around it, team involved in it. So I was in parts involved in it, and coordination was done by some other project leader himself, and I was
Okay.
into the design and the analysis part.
Okay.
So thereafter, my roles and responsibilities changed thereafter.
Okay. Yeah.
Yeah.
Of course. As you get more and more senior, you were interested more and more work on your shoulders.
Yeah.
True. So now, yes, now we will ask you what you were telling us about the challenging project that you were talking about in Gujarat. So if you could
Yeah.
tell us
So
about the challenging project that you did and how you tried to overcome those challenges. Yes, please.
yeah. So this structure is basically a tall building since its height above the ground is like nearly 150 meter.
Okay.
It has two basements. So two basements plus ground plus 32 floors. So the unique specialty of this project is that above 50 meter, we have two cantilevers which are nearly 18 meter projecting from both the sides of the core. So we have a core at the center, and we have two cantilever balance. It's like a balance cantilever, two cantilevers of 18-meter span.
18.
Yeah. So the thing is, above this cantilever, we have it's like a girder. Okay. So we have four stories connected between two girders, and so uh, so that's kind of a floating system actually,
Yeah.
where this cantilever deflections and the moments in the cantilever, there are heavy shears and all involved in it.
Yeah.
So this particular system moved for like 2 3 levels, where we had girder, then four floors girder, four floors girder, floors. So and above that, above the last few four levels, the heights were like nearly below levels were like 4 meter. Then above we had the owners' floor levels. Below were the commercial floors where we had the offices of the
Yeah.
client himself.
Yeah.
And then we had the owner levels, which were nearly 6 meter height, and that was literally floating on the girder.
Girder.
So that did not have a girder at the terrace level because the architect did not want one. So these columns were actually floating on the girder, but they are not considered to be part of the lateral load resisting system. So, and basically, this is an out of code structure. It was the
Yeah.
modal participations are not meeting up as required by the code, 65%. And we
Yeah.
have the second mode as torsion, and the first mode
Yeah.
as sway, and the third
Yeah.
mode as. However, as per the amendment, since it said that the large we have below levels, the podiums are quite large. Okay,
Yeah.
so as per the code, the amendment, there was a clause mentioned that the 65% and the fundamental time period, the difference between the
Ah,
first two modes, can be ignored if we have very large podiums. But
correct.
still, uh, where we have another team who's having some kind of experience in performance-based design.
Okay.
So, and he has a super fast computer, so he would be exploring on it. This is still in a concept stage kind of a project. So
Okay.
there needs to be a lot of research work done on it because of these huge cantilevers and heavy moments which would be transferred onto the main core of the structure. So
Correct.
it's like 32 floors it has, but it has two 18-meter by
Yeah.
25-meter cantilevers. I mean, 18 by
Cantilevers
25
projecting
is
out.
a bay like. It's like
Right.
an inclined cantilever projecting out with the
Correct.
core is I mean there's a office floor which is horizontally placed, and we have two inclined cores. So it is
Yeah.
something like a diagonally, like a rhombus, like kind of
I
system.
can imagine.
So even the earthquake forces and all these combinations which you use were 30% of EQX and 30%. So those combinations also used because of the inclined non. It's a non-parallel kind of
Correct.
system. So yeah. So and then plus regarding the footings, we have just checked it with respect to dead load, live load, and the piles sizes. It will be actually, as per the soil report, it was said that raft is sufficient, but
Uh,
due to the complexity of the project and it being an important and a unique structure, we had from our end as a team to requested the client that it should be a piled raft system, the raft with piles below the structure. And so, in fact, with the heavy dead loads coming on it, the pile dies were like 1,200 mm, and still
yeah.
we are facing issues with resisting the dead load itself. And now with moment, it will get in more critical. So
Correct.
we are still in the process of working on that
Yeah.
pile system. So still we need to have a larger pile dias, like 2 meter or something, or increased number of piles. So we are taking advantage of the raft, the SBC below the raft as well as the pile capacity. So both together we are taking
Trying.
advantage and designing the foundation and safe. So
Correct.
that's a very complex
Very
procedure.
interesting. Yeah,
Yeah.
yeah. Very
So
interesting. I
it's a
mean,
very
it's
unique.
far more challenging than anything that I have even heard till now. So it's quite
Yeah, yeah,
quite
yeah.
a
So and
project that
it has
you're doing.
even flat slabs also with it. Like
Yeah.
it has a flat plate with drop. So when the client insisted they don't want beams in there, this
Correct.
because of floor to floor height, though being greater, but still there it's like 4.2 meter. But they insisted they wanted a flat system, flat slab, flat plate system actually.
All
And below
all
we
the
have, yeah,
all the nightmare then that structural engineer can have, all those are
yeah,
packed into your project. Flat
yeah,
slabs,
yeah. It's
big
a mix of
cantilever,
everything. It's a mix
high
of
6
everything.
floors. So
Yeah.
everything is packed
So
together
the
into it.
wall thickness itself is 1,500 mm. Uh,
Yeah.
core wall thickness.
Core wall thickness
Yeah,
itself. Oh my God. Yeah.
yeah. So 1.5 meter thick wall. So it's
Very interesting.
quite a heavy. Yeah.
Good.
Mm.
Very interesting. So our best wishes with you that this concept project that you're doing, it turns into a reality, and then
Yeah.
we can probably go and see in Gujarat this structure standing tall. Our
Yeah.
best wishes.
And even more, there's like we have the wind tunnel studies on it because the time period of the structure is itself going beyond 5 seconds as per
Right.
16700. So we have to go for wind tunnel. So we have another wind tunnel consultant who is he has modeled it in his wind tunnel, and
Yeah.
those reports have been shared, and we are applying those wind tunnel forces. And since gust forces are a bit complicated to apply because of the shape of the structure, we
Yeah.
have somehow managed to apply a gust force on it, just
Yeah.
a kind of assumption based on some
Yeah.
assumptions of the areas, because the area is a bit every
Yeah.
time
Of
it
course.
keeps changing.
Yeah.
Yeah, so it's a bit tedious to apply gas, but somehow we have used one concept and applied. And however, as per the applying wind tunnel, the gust forces seem to be more.
Yeah.
And yeah, so there are 24 load cases shared by the wind tunnel
Consultant.
consultant and so. So those have to be applied in ETABs, and we are comparing the base shears of both gust and
Yeah.
wind to check how it is working.
Correct.
So that's another. So
Yeah.
and we have even 2 3 models rigorous analysis have to be done because as per 1670 there's a backstay effect due to large podiums overturning and control that
Yeah.
there's a backstay effect with upper bound modifiers and lower bound modifiers which are need. So we have two different models to design the tower as well as the podium beams.
Okay.
So we need to compare all the
All the
models
results and
to check the design.
developing.
So that's a very large procedure on this. So that's
Amazing.
a kind of a different tall building, which is a
Yeah.
bit on the complicated
Complicated.
side. Yeah.
Very interesting. If our audience has some questions for Arthur, they can just type into their chat box, and we would be happy to take up those questions with Arthur. So, how do you see yourself in next maybe 5, 6 years? What are your uh, plans that as a structural engineer you are having?
Yeah, so like I want to get acquainted with the international codes also.
Yeah,
Uh, Other than the Indian, till now I was acquainted with Indian codes, so I want to explore myself into that and improve my knowledge. I mean, use Excel efficiently and create
yeah,
more complex programs using Excel. So I'm
yeah,
aiming to do that and improve my skills also along with, because now VBA is the in thing in our
yeah.
structural engineering. So I want to improve on that and yeah, so
Do
gain
you
some
know
more.
where to learn VB? Because I myself I'm trying to learn VB. So where do you?
No, I have not. I have. I had attended your course, so some inputs are from you.
No, no,
Yeah,
I
so
actually want to
I'll
learn
go through
Visual
that
Basic.
again and try
I
to,
I'm trying
because
to
I'm
ask so
inspired
many
by my
people.
project leader. He himself was he's an expertise in it. Uh,
Acha, okay.
he's prepared software using that, so I got a bit inspired by him. So and I want to like improve my,
Yeah,
because that your I mean there's this kind of importance you get when you know that, and you
correct.
can gain some speed in working on
Yeah,
projects
yeah. I am
using that.
also trying to learn Visual Basic, but
Yeah, so,
nobody. I'm not getting a credible source to learn from. So if you find one, please tell me also.
yeah, sure, sure,
Oh,
sure.
yes, very interesting. So some message you would like to give our audience, because our audience mainly is of young practicing engineers, people who are new into their careers. So if you would like to give some message from your side.
Yeah, so like for the freshers and all, they should improve their basics and fundamentals on SFD, BMD, and also other than just blindly taking the forces from software, compare the results manually also, and try to gain a feel of the structure and the behavior of the structure, and try to like even the earthquake forces, how it is transferred and how you do it manually. Just try to gain some uh, even steel structures. Like if you do it in stat, then there are many formulas given in the code. So compare those forces with the stat capacity so that you have a confidence that you're on the right track. And that's what I
Yeah.
have learned from you also a lot in that way. So
We have also learned from our seniors all these things.
yeah,
Yeah.
yeah. So
Uh,
it was a good thing.
Very interesting.
So that's
So
my
our
advice
audience,
to you there.
if our audience has some question for Arthur, or if you so Arthur, be on the stream. What we will do
Yeah.
is we will go to our next segment, that will be an open discussion that we usually have. So if we have any questions for Arthur on his specific project that he highlighted, or if you have general points for discussion, I think we can take them up now. So, people are interested in knowing more about your cantilever, the large cantilever that you are doing. So,
Okay.
before that, Atif is saying that even his MTech project was on the wind tunnel testing. As you,
Yeah.
he also did his MTech thesis on, or dissertation on, wind
Okay.
tunnel testing. Ajay ji is asking what pile capacity you require. I think that is related to the 1200 dia or 2 meter dia pile you were talking about.
Yeah. So I had done that. Uh, cities, I can't remember the value exactly.
Okay.
It was done
But you
way
were going
further.
for
But
end bearing piles you were providing in your project?
yeah, in bearing piles.
Okay, okay, okay. Then Rahul is saying same. This same is, I think, in that context when you were saying that you were trying to learn Visual Basic VB for Excel. This same is
Uh,
in that context. Yes. Parth is saying amazing project. Uh, Magaj is saying, how did you deal with such large cantilevers? So, what were the basic? If I could put this question in a better way, what were the checks
six.
and the criterias, both serviceability and ultimate criterias that you applied for that large cantilever? If you could tell us.
Yes, so we were basically actually checking the tip deflections to be within the permissible limits of L by 250 as per the code.
Yeah.
And also, there were high shear failures in these girders, but
Yeah.
we are planning to provide a structural steel plate inside this to increase the shear capacity of the girder beams.
Correct.
So using the steel shear strength formula, and the thickness of the plate will be determined accordingly. And
Yeah.
accordingly, shear studs will be provided based on the horizontal shear stress diagram.
Yeah.
So that's how we will increase the because it's very.
Your
I mean,
video, your
though you
video
keep
has
it,
stuck up. Arthur, your video has stuck up.
acha,
Yeah. Just uh,
is it now? Am I audible?
no, you are audible, but your video seems to have stuck up.
Oh, okay.
Uh, the window has frozen.
Acha. Mm,
Just try to join again, maybe.
okay, I'll leave and join again.
Yeah. Very good. So we are facing some technical issues. Let Arthur join back once again. In the meantime, if there are any other points we would like to discuss, Magaj was asking why failing beam members in E-tabs gives wrong shear calculation. No, so as I told you, it's not a wrong shear calculation. They are giving calculations for two-legged stirrups. Yes, Arthur, please continue. So the question was about the
Oh.
cantilever and what all checks you applied for that big cantilever.
Yeah, so the main thing was the deflection actually.
Yeah,
Other than that, we other than that we check it's modeled as a shell element the in ETABS itself as a deep
okay.
girder, which is nearly 3.6 meter uh, height.
Yeah,
So the moments and the shear forces are checked, and the design of the girder is checked. However, as I mentioned before, there are shear failures which are not sitting within the permissible limit of 4 Newton per m square.
yeah,
So yeah, so the grades are quite high. Still, we have a shear stress limit of 4, but
yeah.
we are providing shear plates within the beam, and it's 1,500 thick. So there's quite a lot of space to put in
Space.
a steel plate, which
Right.
will
So
not
did you consider the
have.
possibility of providing an encased steel beam itself, or uh,
Yeah, a steel beam inside it. Yes,
encased steel beam? Yeah.
a
So
steel
did you
plate actually, but we would be providing flanges also on the top of bearing
correct?
at the ends. Yeah,
Right.
so main is the web which will play a role in resisting the shear, and
Okay.
to get a composite behavior, the studs will be provided. But
Correct.
however, we won't be going into the composite analysis of that beam with the steel plate.
Right. Ah, of course. Yeah. That you
Yeah,
cannot
it's
do.
that it's more. Yeah.
Yeah. Parth is joining from Pune. He's asking any specific provision for long-term deflection.
Yeah, so long-term deflection that we would be basically checking as per L by 250 as per the code.
No, so
And
were you taking the elastic values or were you applying some modifiers in your model for checking out the deflections?
so we are applying the earthquake and the wind, the serviceability strength
Modi-
modifiers
Okay.
of 0.35. In
Yeah.
it's like considered as a spandrel beam, so we are using 0.35 as the F22 and F12 and all that M11 M22.
Yeah.
So we are considering those modifiers in this spandrel to check the deflection. It's
Okay.
yeah. So we actually consider it as serviceability and strength modifiers separately, but for
Okay.
deflections, we are using the serviceability modifier checks.
Yeah. So engineer Rais Bhatt, he's joining us from Shopian, Kashmir. He's asking how to. Okay, so about deflection. So people are more interested in knowing how you are able to control the deflection of that large cantilever, because that is always a
Mhm.
pain point
Yeah.
uh, in cantilevers. So I think you took this question, controlling
Yeah.
deflections.
So, and also for the long term effects, like beyond a certain amount of years, we have arranged the columns below at the podium level, since it's a concrete structure and it'll be heavy, and of course we'll have cracks and not structure, but there'll be chances of a settlement at the tips.
Yeah.
We have after a certain amount of, so to control that serviceability criteria for long term purpose, we have arranged the columns at the base level, like
Huh.
up to the ground, in such a way that these tips match with that, and we'll be providing steel columns
Oh.
between the
Yeah.
so that structure won't go wasted. Otherwise, the structure will be a
Ah.
waste, and all the
Yeah.
money
If
goes in.
Yeah, yeah. Acha, so
So
in
we are
future, if
providing.
if it is a long term,
Yeah,
if it is
it
there,
will of course
yeah,
have its own.
yeah,
It gets old. So as the structure gets old, you'll have
correct.
settlements in the. So to control that, we would be providing steel columns at those cantilever tips.
So it would no
To,
longer remain a cantilever. It would be a
yeah,
propped
it
cantilever.
will be, but the structure will be useful. I mean, it
So you
won't
have
go
a,
in.
yeah,
So you
yeah,
don't have to
interesting.
reconstruct everything again.
Yeah. So you have a plan B
Otherwise,
for structure
so
in place.
that's an alternate plan in place.
That is interesting. Yeah, good.
That's a
Vertical acceleration is another interesting point about this large cantilever. So, did you apply vertical earthquakes, or what criteria did you follow for uh, specifically the vertical acceleration of that cantilever?
yeah. So spec Z, the vertical earthquake was applied on it, uh, but we just checked the the acceleration of the structure with respect to the overall, with respect to the gust forces, and that was with respect, and that was as per the formulas mentioned in the wind code IS
Yeah.
875 part 3. So there are acceleration formulas, and that would be within 0.15 for as per 16700 meter per second square. So that particular limit was within it. So we had just checked that, but vertical acceleration of the particular beam, we haven't done that yet.
Okay.
I mean, I think he's talking about even that
Vertical
five
acceleration.
times
Yeah, yeah,
five
five
times
times. Correct,
five
correct.
times yes.
Yeah,
So we need to do that for the design actually.
yeah.
While designing it, it's not a
While
serviceability check, as in, but we are not check the vertical acceleration as such.
okay. And last question from him is, you have taken it as him or her, I don't know. You have taken it
Yeah,
as shell elements or line elements. So you said you modeled it as
yeah,
a
it's
shell.
modeled as a shell element, as a spandrel beam,
Oh,
spandrels or spandrel labels have been provided.
wonderful, wonderful. So I think this was a good question answer session that our audience had with you. And
Mhm.
as with others, I was also interested about this challenging project that you are doing.
Okay.
Uh, Good, very good. So thank you for joining.
You're most
There's
welcome. Anytime.
Yeah, there's one question that was asked to us. Curious to know more about the thumb rules. So this was the question that had been shared to us on the Google form. So curious to know more about the thumb rules that are being followed in the construction industry. Arjun Shetty is asking. He's joining from Bangalore. Also, what are the thumb rules that you are following in your day-to-day projects? So I think there are a lot of thumb rules that we follow, but if the question has to be more specific for a specific answer, I mean, after a while, I mean, complex design calculations can also be converted into thumb rules. So if you have a lot of practice doing those things, even complex calculations become mostly like thumb rules. So uh, uh, I don't know if the question is more specific. Perhaps we can answer it in a better way. Parth is asking, he's saying taking deflection from ETABs with serviceability modifiers and comparing with. So he's basically asking you about the long term deflection, continuing his question that he had asked before.
Mm.
Taking deflection from ETABs with serviceability modifiers and comparing with span upon 250, when long term deflection can be 6 times elastic deflection. Most okay, so this is a general question he's asking, not specific to you. So he's saying that taking deflection from ETABs with serviceability modifiers and comparing it with span upon 250, when long-term deflection due to creep, shrinkage, all those effects, sustained loading can be as high as 6 times elastic deflection. So should not a more stringent deflection limit be set? Yeah. So especially for cantilevers, when
Mm.
the long-term deflection can be much higher, many times higher than the short-term elastic, even with even if you are assuming a cracked behavior by applying modifiers, still the long term deflection can be very high, correct? So should not a more stringent limit be set? I agree. Maybe the codal committee looks into this, but these people have looked into it by providing that steel column he was talking about, so they have a plan B in place. So if their
Yeah.
long term deflection goes out of limit, they have a steel column below the tip. I mean, they have that possibility that later in the future they
Yeah.
can just
So
put up
the
that
load
steel.
also, we have
Yeah,
in the future we have considered another model where these foundation will be uh, designed considering those loads from the uh,
steel.
cantilever.
Even your cantilever will start behaving as propped cantilever, so that also you have
Yes.
designed for.
Yeah. So that also we have another model to be
Ah,
checked in that way. Future
yeah,
post construction, it's called like
very
post
interesting.
construction model.
Yeah,
So
very
there
interesting.
are many things to be checked.
Good. So thank you for joining. Good discussion that we
Mhm.
had with you, and
Yeah.
all the best wishes to you for
Thank you
your
so much.
future. And we
Thank you.
hope to see that structure coming up in
Yeah.
wherever you are
Hopefully.
building it. Yeah.
It's a long
Thank,
time for
yeah.
the process. Yeah.
Thank you for joining. Bye bye.
Welcome, sir. Bye, sir.
Bye.
Thank you.
So that was Arthur joining us from Mumbai. So it was good to hear from him, and that's all we have for today. So thank you, and thank you for taking out time on a weekend and joining us. So that's it. Next time when we will meet, we would be meeting you after Diwali. So have a good festive season, all of you, and we will meet you now on I think 29th. Yes, so we will try to conduct an episode on 29th after Diwali. So have a good festive season. That's all we have. Bye bye and take care. Enjoy the festivities. Bye bye. Good night. I'm just looking for the. Thanks for joining, plate. Yeah, thank you for joining. Bye bye.